3 on chapter 6 through 8, which will be on October 24th to 28th. The chapter quizzes will close at that point. In conjunction with this, we have labs 6, 7, and 8. And for chapter 6, which starts off section 1, is work, which is defined as force times distance, where it's a maximum if F and D are parallel, so moving in the same direction. Units of work are Newton meters, and we'll introduce the units of joules. So that's the case there. Again, when we define work, we do work on an object and accelerate it. That object, because this is also going to be units of joules. So the work done gets it going. It has kinetic energy of 1/2 mv squared, where m is the mass and v is the speed squared. So that's kinetic energy. Again, I'm not going to spend too much time in any of these sections because I've talked about that. But this is section 6.3. Section 6.4 deals with potential energy. PE. And the kinds we have here are 6.4 and 6 is gravitational of mgh. G is acceleration of gravity, h is the height, and for a spring, potential energy is 1/2 kx squared, where k is the spring constant, x is the distance the spring has been pushed. So in both cases, these are the types of potential energy you have, which then can be converted to kinetic energy. We've talked about this a number of times as far as that's concerned. So that's the first part of chapter 6. In 6.6, we have in a conserved, where energy is conserved. Then the total energy, TE, is potential plus kinetic, which stays constant. So if you drop a ball, you lose potential energy but gain kinetic energy. The oscillating spring, it goes from back and forth, potential, kinetic. Same as with the pendulum. It swings back from potential to kinetic, potential, kinetic, and so on, but this stays constant. We have lab 6, which related to that concept of potential and kinetic energy. All right, so those are the expressions there are concerned. So keep in mind these parts. And I'll see what else we have here. And for the last part of chapter 6 is, I will erase this part up here. All right, the last section is power, which is in units of watts. And this is work over time. So this is in joules per second, which is a watt. Again, if you do climbing 3 flights of stairs for a person, same amount of work, but if you do it much faster, you're going to be using more, you're generating more power, but you do it over a shorter period of time. So that is chapter 6 as far as those expressions are concerned. So that's summary for chapter 6. Moving on to 7. We kind of just talked about this with chapter 8. So this is chapter 6. Again, not a whole lot of detail to it. chapter 7, we have momentum, P, is given times mass times velocity, all right? This is a vector, so it makes a difference whether you're going plus this way or plus that way. So if you're going, this would be plus, moving that way, minus would be that way. So the sign makes a big difference, right? It's not just a number. It's not like 50 kilograms. 50 kilograms doesn't matter which way it's going, but momentum, much like velocity, depends on the direction. So that's section 7.1. Conservation of momentum. This is 7.2. And I've been through that, is momentum before equals momentum afterwards in a collision. And the two types of collisions we had are elastic and inelastic. Right? An elastic collision, kinetic energy before equals kinetic energy afterwards. And an inelastic collision, like when they collide and stick together, kinetic energy before is always greater than kinetic energy afterwards. So energy is lost in the collision. If it's an inelastic collision, this is the basis of lab and basis of chapter 7 as far as that is concerned. All right, we then had the two types of collisions. Elastic, where like one ball hits of equal mass, hits, the other stops, and the other one goes off. Inelastic, it collides, and they both go off together. So those are the two extreme cases we're going to be doing there as far as that's concerned. All right, and we have our equations with that. Inelastic collision, and M1 V1 plus M2 V2, and this case equals M1 plus M2 V final. So depending, you'll be given all of these. Based on that, you can figure out what the final velocity is there. All right. We talked about collisions in section 7.5 in elastic. This is also part of section 7.5. The kinetic energy before and after is going to be the same. So, but it's relatively complicated trying to figure that out. So we won't be doing any quantitative problems related to that concept. All right, and find more equals momentum afterwards, where you can find the final velocity. And then the last part related to this concept is the ballistic pendulum, using this, which is the ballistic pendulum quiz. If you haven't done that yet, and this is a case of I have a mass, a big mass, a little small mass of a bullet, hits this, the block rises up a certain height, h, and based on that, how high this thing rises is potential energy. From there you can go back and figure out what the kinetic energy was. From there you can find out how fast this was moving to begin with, and then from there you can find out the initial velocity of the bullet. So that's the ballistic pendulum. Okay, and that's section 7.6. We're not going to do anything in 2 dimensions in this chapter, and we're not going to do anything on center of mass for this chapter. So 7.6 is the last section for here as far as that's concerned. Okay, so moving on to chapter 8 then. So I'll leave this up a minute. All right, chapter 8 All right, what we have there, we have the concept of rotation, rotational motion of theta, omega, and alpha. Been through all that. Relationship between the two is, this is x over r, this is v over r, and this is a over r, where we have the angle is defined again to the x-axis, rotating counterclockwise, and this is r in x. So this is in radians, radians per second, and radians per second squared, as far as that's concerned. So that's the expressions there. The relationship between linear and rotation is that way. Relation between frequency, cycles per second, and omega is 2 pi, omega over 2 pi is a frequency in cycles per second, and the period in seconds is 1 over the frequency. So if you have a frequency of 10 cycles per second, the period would be 1 over 10, or 1/10 of a second. All right. And I had section 8.2. All right. Linear motion equations. I'm not going to put those up again because I did that in chapter 8. And rotational motion equations. All right, basically they're the same, except instead of x you have theta, instead of v you have omega, and instead of a you have alpha. So basically the same sort of thing. That's part of section 8.2. 8.3 we're going to skip. I'll leave that up here. And then we have 8.4, which is torque, which is defined as tau is F times R, where again, force is perpendicular, this is F, and so torque is F times R when F and R are perpendicular to each other. So that's units of torque, and examples related to that. We have the equivalent for Newton's second law of motion for rotation, which is torque is I times alpha, where I is the moment of inertia. And we did that comparing examples of a hoop or a ring, a disc, and a sphere. All right, these three different ones, which one go faster, which one go slower. So again, this torque is given by that expression. And then we have kinetic energy, right? 1/2 mv squared, while for rotation, it's Ke is 1/2 I omega squared. As far as this is section 8.7. And then the final section, section 8.8, is conservation of angular momentum, meaning L, which is given by I omega, L omega before, which is I before omega before equals L after, which is I after omega after. So if you spread out your arms so that this is greater than that, so A is greater than B, then B will be greater than A for it to be constant. So these two will be equal. All right, for conservation of angular momentum, I had the example of the figure skater, comet, and such. All right, so those are the examples there of angular momentum. So, okay. All right. And that is chapter 8. As I said, the test will start on the 24th. You'll have to the 28th to do it. Be approximately 20 multiple choice questions, 2 short answer problems. And you get 1 attempt at 100 minutes. All right, so that's the questions there. You should be all right for that. And